Hey, I'm here to tell you about 2015 number 2, a pretty great free response question. This is up there on the list of my favorites. We've got a dart that is launched up at 10 meters per second, 30-degree angle, and it's going to lodge itself into this block, which is free to swing like a pendulum, simple pendulum. This is 1.2 meters, the length of that, and we're interested in, at some point we're going to be interested in finding the angle here that it swings up to. Alright, so there's some details that I'll pull out of the problem as we go. So for part A, determine the speed of the dart just before it strikes the block. Well, this is launched at an angle, so just making a little diagram. This is not a physical triangle here. This is not like some triangle that represents where it's going for any sustained period of time. It's just the little vector triangle to break this into components. Now the sine of 30, this component, it's just 1/2, and then that would be the constant horizontal velocity. And then here we have the cosine component. I'm looking around for where's my calculator. I do believe that that's 8.7, but where's my calculator? Let's see if I can find it real quick. Got it. Make sure that I'm in degree mode. And so I need to do 10 times the cosine of 30, which is 8.7, 8.66 if you like. I'm just going to keep 2 sig figs there. So that's the, oh, did I mess these up? Sorry, that's not constant. This is the initial, sorry, while I was looking for my calculator, you're probably wondering if I'd lost my mind there. That's the initial vertical velocity, and the constant horizontal velocity is the 8.7. So thing we need to remember here is that in projectile motion we have a constant horizontal velocity, and this will immediately start changing. But right at the launch, that's what we got. So they want to know the speed of the dart just before it strikes the block. Well, according to their description, if you read carefully, it hits this at its peak. So at the peak, the y velocity is 0, right? It's reached the top, but this is still constant. So the speed of the block right at the peak is just the constant horizontal velocity. It always has that horizontal velocity. I don't need to make a vector triangle or anything because this component is just 0. So it's just that. B, calculate the horizontal distance between the launching point of the dart and a point on the floor directly below the block. Well, they want to know what this distance D is right here. So if we just knew how long it took it for there, what the time to get from here to here, then we could just do easy velocity is equal to distance over time for the constant horizontal motion. So I think I need to consider the vertical part and figure out how long it's going to take to get to the peak. So its initial velocity is 5. At the peak, its vertical velocity is 0. The acceleration is negative g, negative 9.8 meters per second squared, and I'd like to know the time that it takes it to do that. So that's just Vf is equal to At plus Vi. So So the time there is going to be 5 divided by 9 point. It's about half a second. And you're actually allowed to use 10 here. If you like to do that, you can. I usually just use 9.8 because we're all calculator enabled and everything. 5 divided by 9.8, just over half a second. So 0.51 seconds. And probably if you look at the scoring guide, they have that you could have time equals 0.50 seconds if you used 10 meters per second squared as the acceleration of gravity, which you are allowed to do. Oh, but that's not the answer. Sorry, I probably shouldn't have boxed that. How far does it go? In the horizontal direction, I know that the distance it goes here is equal to the constant horizontal velocity times time. So my distance d is equal to 8.7 meters per second times 0.51 seconds. So about 4.44. I've been using 2 sig figs, so I'll stick with that. So 4.4 meters. That's how far it goes. Calculate the speed of the block just after the dart strikes. So I've got a block here, the dart's moving into it. Now you might think, well, that's going to kind of rotate here, but right at the instant when the dart hits it, we're just talking about conservation of linear momentum because the initial velocity of this block will also be this way. If you do this with angular momentum, it should still work. That you should just get that the 1.2 distance from the axis, that's going to cancel out on both sides. I'm just going to use linear momentum. So initial momentum is equal to final momentum. Important to write that down. So that's mass of the dart times its initial velocity, which is just that constant horizontal velocity, is going to be equal to the mass of the dart plus the mass of the block times the initial velocity of the block. So let's see, what was the mass of the dart is 0.02 times 8.7 is equal to dart plus block is 0.12. So the velocity of the block right after the collision is equal to 0.02 times 8.7 divided by 0.12. About 1.5. I'm using 2 sig figs here. You could use 1 or 2 more if you want. Calculate the angle theta through which the dart and the block on the string will rise before coming momentarily to rest. So the fact that it's going up and it's changing its height should be a cue to us that this is an energy problem. So the energy that it has, its kinetic energy, is going to turn into gravitational potential energy. There's going to be a little bit of trig involved here, but the first thing I'm going to do is just figure out what the delta H here is, see how high it's going to go. So I have 1/2 mv squared plus equals mgh. The masses actually don't matter, so I'm not going to worry about that. And the height that the block is going to attain is v squared, that initial velocity, so 1.5 squared over 2g. Be careful about those parentheses on the bottom of fractions there. It's a careless rookie mistake there. Not to do that. All right, so 0.11 meters. Now I need to find the angle. So we've done this exact trig problem a few times before. I hope you remember how to do it. So I've got this 1.2 meters, and I know that it's going to go up by 0.11 here. But of course this is still 1.2. So the angle that I'm looking for here, this from here to here is 1.2 minus 0.11. So this side right here is 1.09. So the angle I'm looking for, the cosine of that, the cosine of theta would be equal to adjacent over hypotenuse. So the cosine inverse of this. Let's see what that gives us. The cosine inverse of 1.09 over 1.2. So that's about 25 degrees. And I'm going to take a quick little peek at the scoring guide here and make sure that I haven't given you any bad information. Their answers are slightly different because they rounded this to 1.4 because I kept another decimal place here, and that made this come out to 24 degrees, but we're good, that's fine. Not a problem. And then part E, they want to know that the block then continues to swing as a simple pendulum, and they want to know how long is it going to take for it to go from here to there and back again. Well, the period of a simple pendulum on your formula sheet, 2 pi times the square root of L over G. So that's 2 pi times the square root of L over G. That's equal to 2.2 seconds. But that's not actually what, they're not just asking what's the period. They want to know how long it takes to go from here to here and back again. That's actually half of a period, right? A whole period would be from here through the whole cycle and back again. So this from there and back, that's a half a period. So t over 2 is equal to 1.1 seconds. That's what we're looking for. I think, let's see in the scoring guide real quick. I think they gave 2 points. Yeah, they gave one for doing this and then the second one for realizing that you're just looking for half the period. All right, and last part. They love these with the what would happen, increase, decrease, or stay the same. So in a second experiment, a dart with more mass is launched at the same speed and angle. Dart collides with and sticks to the same wooden block. So let's just, before we even look at what the questions are, what would be the same and different? If the dart has more mass, it doesn't change the trajectory of it, right? The horizontal velocity would be the same. But when it hits here, since it has more momentum to start, it's going to have more momentum after the collision, and that means that if it has more momentum after the collision, and this had the same mass, that it's going to swing a little higher, right? If you launch something heavier into this at the same speed, that's going to make it swing a little higher. So that's actually part one. Would the angle theta increase? The angle theta would increase, and our justification would be so greater initial momentum means greater final momentum, which means a greater v block, which means since the velocity of the block, since our height depended on v squared, what that means, greater h. And that means greater theta. That's one way to kind of logic your way through those things. You can actually appeal to the equations and like, you know, do some work there if that makes you happier. Would the period of oscillation after the collision increase or decrease or stay the same? Well, the period of a simple pendulum is equal to this. This is not dependent on the velocity or the mass. So we're changing the mass of it because we fired a bigger dart, and that made it go faster since we fired it at the same speed per our logic here. But the period of the simple pendulum, it doesn't depend on either of those things. It only depends on the length of the pendulum. That's it. And what planet you're on, I guess, if you want to fuss about that. So that means that the period would be the same. All right.